So hopefully this video is a little bit of a review in terms of making a buffer, but you might be a little rusty. It might have been a while, and maybe you've never even made a buffer before. So I'm going to walk you through a couple different examples and then think about how you would actually make this in a lab. First example is just generic. So for example, you're in a lab, you're doing some research. If you're in my lab and you're doing research, you're making buffers all the time for different electrochemistry solutions. So I might say, hey, make a pH 5 buffer using acetic acid and acetate. And that's all I tell you. And so you've got to think about how you might compute this and then how you might make it. So we'll go ahead and use the trusty Henderson-Hasselbalch equation here. But of course, we need to know the pKa of our weak acid system, which is acetic acid. So you just look that up. You can Google it, or you can grab it from the back of your textbook, or one of the any million places that stores pKa values. You'll find those pKa values may differ slightly. It's totally fine in this class. I'm never going to fault you for grabbing a pKa unless it's a completely wrong pKa. But back to your textbook says the pKa of acetic acid is 4.76, so that's the value that we'll input for the pKa here. We are shooting for a pH of 5, so that's what we're going to input for that. That'll allow us then to compute what the ratio of A minus to HA would be in a situation where the solution is pH is 5.00. This is also a good time, especially in this course, because maybe you didn't really think about developing an intuition for buffers when you learned it the first time, but since this is the sort of second time around, this is a good time to really think about what that means, right? Because if the pKa is 4.76 and the pH that we're shooting for is 5.00, what do we know about the pKa? Well, we know from the implications of this expression that the pH is equal to the pKa when A minus is equal to HA. So that's when the pH would be 4.76, right? If those two things are equal, then those two things are equal. This is not the case right now. We have something that's higher than 4.76. So what does that tell you about the ratio of A minus to HA? Well, if they're equal, if the pH were 4.76, then these two things would be equal. Now that the pH is slightly higher, what that means is, and it's more basic, is that you have more of the base in solution compared with HA. So we would expect the ratio of these two things to be greater than 1, meaning there's more A minus than there is HA. So this is a good way to start thinking intuitively about this. If we had a pH that was less than 4.76, maybe it was 3.5, then we'd expect the ratio to be less than 1. We would have more acid in the system to create a pH of that nature. So if I write that out fully, I'll have pH 5 equals 4.76, which is the pKa plus log base over acid concentrations. So I subtract the 4.76 from the 5, I get 0.24 is equal to log of the ratio of those two species. So we need to solve. So to get rid of the log, we'll take 10^2 each side of the expression. So 10 raised, or 0.24 raised to 10 here. And that will eliminate the log term, and that will be equal to the ratio of the base to the acid. And compute that, that gives you 1.74, which fits our original suspicion that the ratio of these two things was going to be greater than 1 simply because the pH was greater than the pKa. We knew there had to be more of the conjugate base at equilibrium than the acid. I like to think about this too. When you have a ratio and it's equal to 1.74, what that really means is that you have 1.7 parts or 1.74 parts of base for every 1 part of acid. That helps me really understand what is going on here. The other way to think about that is the proportionality of in the system of A minus is going to be 1.74, because there's 1.74 parts per 1.74 plus 1 part, or 1.74 over 2.74. Because there's 1 part of HA and 1.74 parts of A minus, then the percentage of the system that's A minus is going to be whatever that fraction is, which is 63.5%. So at equilibrium, what that's saying is that 63.5% of the solution will be A minus, 100 minus that, which will be 46.5%, will be in the form of HA. That's a really intuitive way to start thinking about these buffers. So what we did just now was compute the ratio of base to acid, but that gives us really nothing with respect to how to practically make it in the lab. If we needed to make this in the lab, we'd have to have a little bit more information. We'd have to know what volume do we need to make, and we'd also have to know what concentration do we want the buffer to be at. And by concentration, I mean what is the overall concentration of the conjugate acid or conjugate base and the acid together. So that means in this case, the example I'll do is let's do this for a buffer that's 500 milliliters, so 0.500 liters, and I want to do this at a buffer concentration. So I'll write this as the total buffer concentration, which really means the concentration of HA plus the concentration of A minus. I want that to be 1.00 molar. So if somebody says make a 1 molar buffer at pH 5 and make a half a liter of it, this is the constraint. So how do we actually do that in the lab? So you'd go and you'd start by grabbing a 500 milliliter volumetric flask, like the beautiful picture I have drawn here. So of course the benefit of that is it's going to give us exactly the solution volume we need, which is important here. So we've got the volume taken care of. How do we compute what we need for a 1 molar buffer? Well, we can do it two different ways. The way I'll show you is the first way, which comes back to this 63.5%. So we know that the ratio, I'm not going to recompute the Henderson-Hasselbalch because it's the same at 5, so it's what we're talking about is this solution. So we know that from that solution, the ratio of conjugate base to acid is 1.74 parts to 1 part, or 1.74. And then I said, well, what that really means is that there's inside of this beaker, there's going to be, or inside of this volumetric, there's going to be 1.74 parts of A minus for every 1 part of HA. So what that really means, if we want to think about the fraction of the solution that's either A minus or HA, then I need to say, well, for A minus specifically, the percent A minus is going to be 1.74 parts of that over the total, which would be 1 plus 1.74. And we said that if you multiplied that by 100, that gives you 63.5%. And then sort of taking 100 minus 63.5, that gives us the percentage of HA, which would be 46.5%. We could have also just solved it by taking 1 part over 2.74 parts times 100. Either way would have given us that answer. So what utility does that have? Well, if we know that the desired concentration is 1 molar, then we can figure out what concentration of each A minus and A is required here. So all we would need to do is take the 1 molar times 63.5%, and we would get our value. So what that really means is, if I do this in red, we would have 0.635 molar as our A minus concentration at equilibrium, and we would have 0.465 molar HA at equilibrium. Okay, so there's something important about this. So I should finish my thought really quick. So now that you know the concentration of these things, and you know that there's 0.500 liters, we know the moles per liter. We multiply each of those molarities by the volume. You have the moles of A and you have the moles of HA, and depending on if they're solids or liquids, you figure out what the mass or the volume of each of those are, and you add them. And then you bring it up to volume with water up to the 500 mil point. That's it. That's a simple way to compute this. One of the challenges here, and let me tell you, so if you take this and you make it up in this volumetric, one of the challenges with this is going to be that once you put a pH electrode in here and you measure it, it's not going to be 5.00. What's the reason for that? what are we assuming in this entire process here? The major assumption with using the Henderson-Hasselbalch equation like this is that we just determined that there's a fraction of each of these things, right? And we say that at equilibrium, these are the concentrations in order to sustain a pH of 5.00. But at the same time, I'm adding a weak base and a weak acid to water. Both of these things are going to re-equilibrate to some degree, right? The HA is going to dissociate to make H plus and more A minus, and the A minus is going to react with water to make more HA and some amount of hydroxide. And so there will be a minor re-equilibration as these two systems move slightly. It may be imperceptible, but it won't be exact. And so you may put your pH meter in here and you get something like 5.05 or 5.12, and it's slightly off. And that can be for many reasons, experimentally and error-wise, but at the same time, it's also from the fact that we're assuming when we mix these things together that they're not going to change at all, that they're not part of their own equilibria, which they are. But either way, this is the standard way, and if you were going to make this in a lab, the best way to do it would be to compute it like this, or in the second way, which I'll show you. Add them to your 500 ml flask and bring it up to volume, and then change the pH to the desired level by having small additions of either a concentrated base, usually NaOH or KOH, if you needed to get it more basic. In this case, if this were our reading somewhere in there, we'd need to add more acid, and so usually we'd have like some concentrated HCl or H2SO4, usually like 1 molar or 3 molar, and then we add a couple drops into this and we monitor it until we get it dialed to exactly 5.00. That would be the practical way to go into the lab and make up one of these solutions. Okay, so the second method starts at the same place. So we would have had to solve the Henderson-Hasselbalch equation and get to this point where we have the ratio A minus to HA, and that's equal to this 1.74 value. And so the second way just uses substitutional algebra to solve for A minus and HA rather than using sort of intuition and just thinking about it fractionally like I did in the first step. Either way will get you exactly the same answer. It just depends on what you like to use and what makes more logical sense. So what we can do here is essentially what we have is x over y equals 1.74. Right? That's the expression, really. And so I can solve for one of those in terms of the other just by simply multiplying the 1.74 by HA. And so what that gives me is A minus is equal to 1.74 times HA. I just multiplied both sides by HA. But we need another equation, obviously, to solve this substitutionally, which we have conveniently up here already written. Right? I know that the concentration of my acid plus my base has to equal a constant, 1.0. So we could write that out again as HA, the acid, plus A minus, the conjugate base. Those have to add up to 1.00. So I have two equations, I have two unknowns. I can solve these two things substitutionally. Easily done. Maybe in this case I could just grab this A minus, since it's already solved for A minus, and insert it here. And so what I get would be HA plus 1.74 H times HA is equal to 1.00. Okay, so what that gives me, if I add those up, and I'll just move up here so you can see it better, would be 1 HA plus 1.74 HA would be 2.74 HA. Make sure you see where that's coming from, because I'm taking one of these HAs plus 1.74 of these HAs. I'm adding them together. That's a positive sign here. That's an addition. Gives me 2.74 of the HAs. That's equal to 1.00. So then HA concentration has to be equal to 1.00 over 2.74. Hey, look at that. That looks pretty familiar to this expression where HA was equal to 1 over 2.74. So it's the same exact result. Once we know the concentration of HA, then which would be 0.465, then we would know we could either plug it in or just take 1 minus that value, and we would know that A minus, then if this is equal to 0.465 molar, then A minus would be equal to 0.635 molar, simply 1 minus that. Either way, these are going to get you to the same result. If you took Chem 108 with me, I would teach you both ways. So these are, I learned the first way, method 1, when I was an undergrad, but I sometimes find method 2 to be more intuitive mechanically for students. So whatever you want to do, they'll get you to the same result.